Hello and welcome to Chapter 2 in Introductory Physics. In this chapter we will be examining the area of kinematics. The word kinematics arises from the word kinema, Greek word for a description of motion. By that we mean motion that occurs can be observed and measured in terms of distance and time, and then calculations made with respect to the speed or velocity and the acceleration of the object, and relationships that can be determined between these quantities, distance, time, velocity, and acceleration, are called kinematics equations. So in this chapter we will be looking at the kinematics and a description of motion that accompanies one-dimensional motion, motion in a straight line. And also, kinematics doesn't really care what caused the motion. In other words, at this point we're not going to be interested in or concerned about the forces, the pushes and pulls that cause objects to move. We're just simply going to accept the fact that some sort of acceleration, velocity changes are occurring, and we want to know, how do we predict where the object will be in the future at a later time? How fast is it going? And what is its acceleration? In your textbook, there is a graph, such as the one shown here, and some data just above that graph. You'll notice it says time on one column and position or distance on another column. Notice that the units we're using are the meter unit from our fundamental units and the second unit also from our fundamental units. So we are graphing on this graph the distance, the object, the position of the object at the time noted. You should place on this graph the data that's given so that you can generate a representation of this motion, a graphical representation that looks as follows. Notice the red line represents where the object is located at 0.02 meters at 0 seconds, 1, 2, 3, 4, 5, and 6 seconds. Now I realize that this is a fairly boring motion occurring because it's not going anywhere. What we have here is a representation of an object at rest. But we can write down a relationship. And you'll notice below your graph there's some questions that refer to this graph. And what we're asking there is, what is the equation, mathematical equation that would describe this motion, where you would write down the symbol x to denote its position, and x would equal what? Well, you're right. That's right. X would equal 0.02. There is no time variable in this relationship because the x is not changing with time. But still, that's an equation that tells you something about where this object is located at all times. The next set of data, which is the second graph on your page, is data that shows the position or distance changing as time moves on. And you'll notice here we have a line, the red line, increasing at a uniform rate. Or as I like to say, it has a constant slope. You recall that slope is the vertical rise divided by the horizontal run. And slope represents the steepness with which this line is inclined. And for a line such as this, we have one single slope. That is, the line has gone up 1 meter. The object has traveled 1 meter in a time of 5 seconds. And therefore the slope of this line would be 1 meter divided by 5 seconds, or 0.2 meters per second. Notice the units on that quantity slope are the actual units on the physical quantity speed. That's kind of interesting, isn't it? Now, what would be the equation that would describe this line? That is, if we write an equation that says the object is located at x at time t. So we want an equation that starts with x is, or x equals, because is the equal sign in mathematics. So x equals something times the time. Notice the time unit is in there because x is changing with time, and therefore as this variable grows, x must change with it. So what would be the coefficient in front of the time if we were to write x equals something times time? We would see, well, in order to have the units of time cancel so that we end up with the units of meters, we need to have a quantity in front of the time that is in meters per second. And we already have that, don't we? We have the slope of the line, 0.2 meters per second. So we could write an equation, rather than this graph, that gives us the same information, that says this object is located at x equals 0.2 times time t in meter units at all time. And so even though we don't know where the object is at 6, 8, or 100 seconds, the equation will predict for us where the object would be located if these conditions continue. So in fact, our mathematical relationship is predicting the future for us. Now, in the second example, we had a situation of a constant slope, which represented constant speed, so that the distance traveled increased at a uniform rate. Notice that the data for the third set of motion, when plotted, becomes a curved line. Notice that for the first second, the object travels 1/10 of a meter. And then during the second second, the object travels 2/10 of a meter, going from 0.1 to 0.3. And during the third second, the object travels from 0.3 to 0.5. And during the fourth second, travels from 0.6 to 1. So we have an object which is covering more distance each second than it did the previous second. This is called accelerated motion, where the speed is changing. Notice that the graph represents a changing slope. That is, from 0 to 1, the slope is more gentle than from 1 to 2, or 2 to 3. To determine the slope, we would draw a tangent line at each point and calculate the rise over run. Now, what we would find if we did that we have a situation here where the speed is changing by the same amount every second. In other words, it is uniformly accelerating. Uniform acceleration means that the value of the acceleration is constant. For example, when you drop something and it falls to the ground, speeding up as it goes, the acceleration of gravity is a constant value. That value is 9.8 meters per second squared, or in a system you may be more familiar with, 32.2 feet per second squared. So all free-falling motion on Earth is uniformly accelerated motion. And anything we calculate using the kinematics of uniformly accelerated motion will apply to free fall under the influence of the gravitational force. So we always want to have an equation, because an equation allows us not only to take the data that we have and model it, it allows us to predict the future for this object. Where will it be at 10, 20, or 30 seconds? Well, in the first data set, we found that x was 0.2 meters. In other words, the object wasn't moving. And then in the second data set, we found that x was 0.2 meters per second times the time. The object was moving in a straight line at constant speed. Notice that in the first equation there was no time variable, or if we were to write that mathematically, we would write down that x equals 0.2 meters times t raised to the 0th power. So our equation had a t in it, but when we raised t to the 0th power, any number or any symbol raised to the 0th power is equal to 1. So you could write the equation x equals 0.2 times t to the 0th power for the first data set. Now in the second data set, with a constant speed, we wrote an equation x equals 0.2 times t to the first power. Remember that that was the straight line inclined at an angle. Now what do you think the equation would look like for this data set? If the first one was t to the 0 dependence, the second one is t to the first power dependence, you would anticipate that this would be an equation x equals something and t raised to the second power. So an equation that is proportional to t squared is a logical equation for accelerated motion at a constant value of that acceleration. Let's look at these equations then. We wanted to give you a conceptual basis behind how one understands the kinematics equations that we're about to show you. First of all, we need to start out with some definitions. We will define the concept of displacement, meaning when something is displaced, it is moved from where it is to a new location, and therefore the distance and direction between the start and the end is known as a displacement. We call that delta x, where delta x stands for the second location minus the first location. The velocity is a derived quantity then, which is calculated by the displacement divided by the change in time. Notice that in terms of the quantities x and t, the change in x is x2 minus x1, and the change in time is t2 minus t1. And similarly, acceleration we will define as the change in velocity, v2 minus v1 over t2 minus t1. Generally, we will set the time t1 equal to 0 because we start our clocks or our timers at the beginning at 0 whenever we're making measurements. So we really don't need t1 in our equations. That means t2 is the only time variable that shows up in our equations, and that always stands for the time at the end of the particular measured motion. So since that's the only time that shows up in our equations, we don't need a subscript 2 on it because we're not differentiating it from 1, and so we just drop the subscript. So here's a set of kinematics equations for one-dimensional uniformly accelerated motion. The first one tells us that the distance can be calculated if we know the average speed and the time that we're traveling. Notice that time is the time at the end point, assuming that their time is 0 at the beginning. If you put t equals 0 into this equation, you get x equals 0, which is where you started. Now, if you think about your own traveling in a car, when you're traveling at 55 miles per hour at that constant speed, and you travel for 2 hours, you know that you multiply 55 miles per hour times 2 hours to get 110 miles. So you actually know this equation already. You used it, but you didn't know it was a mathematical equation. Now, if you are speeding up or slowing down, then your average velocity will be the sum of what you start with plus what you end with divided by 2. For instance, if you start at 0 at a stop sign and you accelerate uniformly to a velocity of 30 miles per hour, then over that distance that you accelerated, your average would be 0 plus 30 divided by 2, which is 15 miles per hour. Now, in reality, you travel the same distance if you traveled at 15 miles per hour throughout the interval that you would if you started at 0 and accelerated evenly up to 30 miles per hour. The third equation in our list here, then, is sort of a rearrangement of our previous definition of acceleration. Remember, we defined acceleration as A equals v2 minus v1 over t2 minus t1. Well, if we use the notation that our beginning velocity v1 will always be called our original velocity, and we use the subscript O or 0 to denote original, then VO is going to be our V1. And then V2 will just simply be the velocity V at that later time t. So if you rearrange that previous defining equation for acceleration, you get this relationship which says V, the velocity at some later time, is equal to V0, the velocity you started with, plus a quantity, the acceleration, times the time. Remember that all of these equations must be in our fundamental units, meters, kilograms, and seconds. Now, the last two equations are very useful. They are actually rearrangements and combinations of the previous three equations that are derived in order to accommodate situations where we know certain information but we don't know other information. For instance, if you look at the fourth equation, you will notice that that equation tells us where the object is. That's x. Where are you located? At a time t. Notice that t is in there as well as t squared. So it's telling you where x is, where is it located x at time t, given that you know how fast were you going at the beginning and what is your acceleration during this interval of time. Now notice we don't know anything about the final velocity. We are only interested in where are you and what were the initial conditions that existed when you started accelerating. So that's a good equation whenever a problem asks for where are you located, how far have you traveled, questions like that. We'll be doing a lot of problems, and you'll have lots of practice with problem-solving strategies. Initially, you may choose the wrong equation. That's okay. If you choose the wrong equation, you're probably going to find you come to a point where you don't have enough information. And that should be a clue that you probably started with the wrong relationship and need to go back and try another one. We'll try to develop some skills in this and show you how to eliminate guessing and make some choices based on good, solid information. Now, the last equation is also derived from the previous ones, but you'll notice the last equation does not have time in it. So if you had a problem in which you were told some information about how far you had traveled, how fast you were going at the beginning, and under what acceleration you were traveling, this equation would tell you what your velocity is at the end of that distance. I realize that it's a v-squared equation, so once you calculate the right-hand side of this equation, you will have to take the square root to find the speed that you're traveling at. But that's okay. It's just written in this form because it's a nice, useful equation, and we don't really want to have a square root in there. That would just look inconvenient. So this is our set of kinematics relationships that we want to use in solving one-dimensional uniform acceleration of an object. In fact, we'll actually use these for 2- and 3-dimensional motion. Now, when you're solving problems, you really need to first identify what you know. So this list of equations should be right next to you, and as you look at a problem and you're reading through the words, you will come to numbers that stand for something, such as 25 meters per second and 1.8 meters per second squared. So as you begin to work with these equations, you will begin to realize that these numbers must be labeled with symbols. So if a number is in units of meters per second, you know that that's supposed to be a velocity, and you will label it with a V. The only question is it the original velocity or the final velocity? Well, we'll be able to tell by the problem. Perhaps the problem says a car starts from rest and accelerates at 1.8 meters per second squared to a final velocity of 25 meters per second. What is the distance over which this car traveled? All right, let's go back and break that problem into pieces. A car starts from rest. Well, if it starts from rest, then that is its starting or initial velocity. That's v0. So go ahead and write that down and label that. v0 is 0 meters per second. Now, the car started from rest and accelerated at 1.8 meters per second squared. What are you going to label that number with? That's right. You're going to label it with the symbol A for acceleration. Very good. Then we said it accelerated at 1.8 meters per second squared over a distance and achieved a final velocity of 25 meters per second. So, the last speed that this vehicle achieved in this problem over this distance was 25 meters per second. That would be our value v. So we have identified three quantities in this problem statement. V0 is 0, the initial starting speed. The final velocity, v, is 25 meters per second, and the acceleration is 1.8 meters per second squared. And what is the problem asking for? Well, the problem is asking for, look at the question mark, and go back from the question mark and see what is the quantity that is being questioned here. And the quantity is, how far did it travel, or maybe words like, what is the distance, or what is the length? Some term that indicates that you want to calculate the number of meters that the object has moved during the interval that we're talking about. Do we know the time? Well, no, we don't know the time, do we? Nothing in our problem at this point has given us the time. Well, that's okay. In other words, you could write t equals a question mark on your paper under the area where you've collected the known values. But do you need it? Well, you might look at equation number 3 or 4 and say, if I don't know the time, I could calculate the time with equation 3, because I know v is 25 and v0 is 0 and a is 1.8. And I could solve that equation for t. That would be fine. And then you could plug that equation for t into the fourth equation using the known value of a and v0 and find x. And if that's what you did, that's fine. Now, some others might simply go to the fifth equation and say, I'm not really interested in the time it took for this to happen. I already know v is 25 and v0 is 0 and a is 1.8. And so I can solve my equation for x by using 25 squared equals 0 squared plus 2 times 1.8x. So there you go, another way of doing this. Sometimes there's different ways to arrive at the same answer. Oftentimes it may take a few more steps with one process, but it doesn't mean it's wrong. So this is an example of using the kinematics equations. We'll be doing lots of problems involving these equations over the next 3 or 4 chapters. You'll get lots of practice. I encourage you to use the homework template that's in your book. With this template, it enables you to write down a short summary statement of the problem, label and identify the knowns that you have in the problem. That means writing the variable x equals, a equals, v and v0 equals, t equals, and so forth, and putting the numbers and units that go with those quantities. And then by looking at those and saying, what is it I'm looking for, you can write down in the next section of the template what equations are relevant to solving this problem. Once you've identified what you know and the equations that are relevant, go to the solution space and work out the answer. Some answers will be relatively straightforward. For instance, as in this previous problem, a one-step approach was to use the v squared equals v0 squared equation plus 2ax and substitute in the numbers and solve immediately for the unknown x. An alternative approach was to solve for the time t from one equation and then plugging that value into another equation, a two-step process. Both are equally valid. But in your solution space, that would be where you would work through the answer, and of course down at the bottom of the page, place the answer. Label the answer with the proper symbol and the units that go with it, and you're done. Following this approach will teach you a discipline for solving these types of problems. Identify what you know, identify what you don't know, identify relevant equations, combine, if you must, equations, solve for unknowns, and get your solution. As we move forward, we will be doing much more of these types of equations as we look at further into one-dimensional and two-dimensional motion.